to the wireless channel. And here we are with Ryan, who's been working a lot on affine types of modulation. And today he's going to give us a nice talk about affine filter bank modulation. In particular, this talk, if I'm not wrong, is based on a recently submitted article that explains this entirely new waveform. So, Ryan, welcome and please take it away.
Hello, my name is Ryan, and this presentation is going to be about a new waveform that we proposed based on an article that we recently submitted to the Transactions on Wireless Communications. So this is the new waveform is going to be called Affine Filter Bank Modulation, and we are going to be proposing this as a novel 6G ISAC waveform with very low PAPR and out-of-band emissions. So let me take a moment to thank our Brazilian colleagues, Henrique, Gustavo, and Bruno from UTFPR, and also Didier from France. So let's jump straight into it. So we can quickly go through an introduction as to why we motivate this waveform, this new waveform. And then we jump straight into the system and signal models. Then we describe the PAPR, out-of-band emissions, and the ambiguity function performance of the proposed waveform. And then we go and talk a bit about the communications receiver and the sensing receiver. So this presentation is going to be a bit compact and not going to take up too much time. So we will skip the relevant mathematics whenever we need to. But of course, all the details can be found in the corresponding journal paper attached. So yeah, as a slight motivation to why we are proposing this waveform, we know that next generation wireless systems aim for typically high data rates and also higher frequencies in high mobility settings. So this naturally gives rise to double dispersive channels, also called delayed Doppler channels sometimes in the context of OTFS. But we know that these double dispersive channels typically degrade the performance of OFDM. And I'm talking about the typical OFDM system here, where you would have a cyclic prefix and a bunch of data carrying subcarriers. And when exposed to double dispersive channels, the orthogonality of the subcarriers breaks down, and naturally you lose performance. So two promising waveforms to mitigate these effects are OTFS and AFDM. So OTFS stands for orthogonal time, frequency, and space modulation, and AFDM stands for affine frequency division multiplexing. So these are two promising new waveforms that have been proposed. And to talk a bit about these two waveforms, so OTFS is a 2D modulation scheme based on the DDW domain, but of course it has a bit of a high implementation complexity due to its 2D nature, and it also does not reach the optimal diversity order in double dispersive channels. When we look at AFDM, we have chirp-based subcarriers similar to OFDM, but the frequencies also vary within the subcarrier, and AFDM achieves full diversity, but suffers from high PAPR and out-of-band emissions. So also, I should also mention that OTFS has a lower PAPR than OFDM, but still typically higher than other waveforms out there. So we want to try to reduce the PAPR and out-of-band emissions. And two examples of this is this DAFTS AFDMA, which is a DAFT spread version of affine frequency division multiplexing, which is similar to DFTS OFDM, which is typically used in the 5G uplink. And of course, you have COCDM, which is a variation of OCDM to try to mitigate the out-of-band emissions. But let us consider now a new player in the scheme. So we're all familiar with filter bank multi-carrier modulation schemes, which have excellent spectral localization and also no cyclic prefix, very low out-of-band emissions. But of course, these systems lack delay Doppler robustness. And they also have similar effects when exposed to double dispersive channels, right? So this fundamental gap that we have right now in the latest related literature is that there is no ISAC waveform with low PAPR, out-of-band emissions, and delayed Doppler robustness. So our proposal is affine filter bank modulation, which integrates this prune DAFT precoding with filter banks and the nice doubly dispersive robust structure of AFDM. So of course, the benefits of this new proposed waveform are its low PAPR, similar to the AFTS AFDM, and low outer band emissions, and of course the robustness to double dispersive channels. So let's start with a system model that we want to use to describe this waveform. So we have a typical transmitter here and a receiver here, and I've termed them both ISAC transmitters and receivers. But so far, what we are going to do is try to describe the waveform from the fundamentals and also build receivers. So this ISAC RX is actually, it can be either a communications receiver or a sensing receiver. And as illustrated here, it's a point-to-point system with P scatterers in the surrounding. And of course, the goal of the ISAC RX, if it's doing communications functionality, would be to decode the data symbols given the channel. And if he wants to do some sensing, the goal would be to estimate target parameters, for example, the delays and Doppler shifts of the target scatterers, and estimate those features from the received signal. And of course, some pilot sequence or preamble. So some preliminaries before we jump into the details are that we are going to consider L subcarriers, K time indices, and out of these L subcarriers, we are going to have L over 2 guard bands. And since we have L over 2 guard bands, we are going to assume that we are going to oversample it and transmission occurs every L over 2 samples. And of course, our grid is going to then be of L frequency points spaced by F hertz and K time points spaced by T over 2 seconds, where T is the time period, of course. And yeah, correspondingly, the bandwidth is L times F with the total interval defined by KT divided by 2. So let's also consider, without loss of generality, to have a set of transmit symbols. For example, we can choose QAM here, and this vector is going to be of size k L over 2 by 1. So the first thing that we are going to do for the modulation procedure to create the AFBM waveform is to do a time frequency mapping with our transmit symbols. So you take our QAM symbols and multiply it with this psi matrix here, which you can then represent as an equation 1. And this psi is actually going to be defined as the chronic product between an identity matrix and another psi bar, which somehow distributes the symbols at the upper and lower levels of the matrix. So this is just a typical time frequency mapping to avoid the inter-subcarrier interference. And next, after we have that, we can now go ahead and do the prune DFT precoding. And the relevant formulation is given in equation 4, where we multiply this time frequency mapped signal, these transmit symbols, by this C matrix, which contains the prune DFT. And of course, after that we also apply a frequency domain 0 padding to this output. And details for that are given in equations 6, 7, and 8 respectively. And this is going to be our second stage where we do the prune DFT precoding and the frequency domain 0 padding. So this also significantly, this is similar to the spreading operation that occurs in DFTS, AFDM, for example, where we try to spread out our symbols in the frequency domain so that the interference is minimized. And the final stage will be the prototype filter, which is fundamental to typical filter bank multi-carrier modulation schemes. And this is constructed as usual to be a Toeplitz matrix, a band diagonal Toeplitz matrix. So that structure is given by G, and we can construct this filter based on for example, practical filters would be, for example, the Hermite filter or the Phi Diaz filter. And the full matrix would look like this. So as I said before, is a block Toeplitz matrix, and the dimension is also specified at the top. So this might seem a bit complicated, but the whole procedure is summarized in figure 2 here, where you see once you get your usual symbols, your symbols from an alphabet, for example, your QAM symbols, you would do a time frequency mapping. You would do a DAFT spreading, and then you would do the IDAFT plus frequency domain zero padding. So this is the main section. And then finally, you would transmit the signal through a prototype filter bank, and you would end up with your time domain transmit signal, which is given by S. So as you can see, the S is going to be composed of your G, your prototype filter matrix, your operations for your zero padding IDFT and the DFT spreading, and of course the time frequency mapping. So this is going to be a final transmit signal in the time domain, given your uh, symbols from your constellation. So this is the full modulation schematic, and this is how you would do the modulation procedure for this new proposed AFBM waveform. And now you have, of course, your receive signal, where now we assume that we have a time varying signal, transmit signal. So we pass it through the double dispersive channel that we have defined, that we have talked about a bit previously. And of course, our receive signal can be expressed as in equation 12. And in this equation 12, the H check is going to be a typical time domain double dispersive channel matrix, where this psi r is a cyclic prefix if you want to use one, of course. And this Z is going to be a diagonal matrix which represents the Doppler shifts, which somehow encodes the Doppler shifts, the normalized Doppler shifts of your scatterers. And this pi is going to be a left shifted uh, matrix that is going to be that depends on your target delays. So this is the typical structure of the double dispersive channel. And of course, we are going to make an assumption here that in these k time slots, that this channel matrix is not going to vary. So we can have the same channel matrix across all of these time slots. So once you put all of this together, we can derive the full input-output relationship, which is given by equation 14, seen here. So you have all the operations described here, the time frequency mapping, the DFT precoding, and of course your filters. And as you can see, equation 14 is now an end-to-end input-output relationship uh, for our signals. And this H effective is going to be the fundamental effective channel of this system. So there's one thing that I have to specify here, in the sense that when we are going to build receivers, it's probably obvious that we can do it in different stages. We can either demodulate, then decode, or decode straight away in the time domain. And this actually depends a lot on the fundamental effective channel matrix structure. And as we're going to see later on, what's going to be more effective to decode is going to be this part right here, which is why I have defined an H bar. And we are going to be using this part, this H bar, to decode and detect data symbols, as well as do radar parameter estimation later on. So the fundamental reason for why we want to do this is because, as you can see on the left side is what happens if you try to use the whole effective matrix defined in the first equation there before that we saw. And as you can see, the gram matrix is going to be very spiky, so it doesn't approach a nice diagonal structure, which is known to be bad when we want to design low complexity equalizers in that domain. But on the other hand, if you look at the frequency time domain, the hybrid, we call it the hybrid time domain matrix, where we process the signals in the time domain. That effective gram matrix looks very spiky, and the side lobes are, of course, also minimized in both cases for the Hermite and the phi ds filters. So this motivates us to consider this hybrid time domain variation for use in receiver design. And before we jump into the receivers, we'll take a moment to look at the PAPR performance and other useful features of this waveform. So as you can see, compared to conventional AFDM, the PAPR of the proposed scheme is much lower. And now would probably also be a good time to point out that the PAPR is dependent on the choice of parameters that you use to build this waveform, that are the C2s, which is also known to be a tunable parameter in AFDM as well. So this feature has not been explored yet fully, because this requires building a multi-objective optimization problem to tune these C2s according to the purpose that you want it to have. For example, low PAPR or low outer band emissions, lower ambiguity function, and so on. but this is relegated to future work. And of course, next we have the outer band emissions, which is one of the places where this waveform really shines, because compared to the typical AFDM scheme, this has a huge improvement in terms of both filters. But of course, the 5DRs being a longer filter performs better than the Hermite filter in the case of AFBM. And this is the ambiguity function performance. And as seen here from the delay cut, you can see that the AFBM waveform has very similar ambiguity function to the AFDM waveform, but the 5Ds exhibits a lower side lobe level than the other two. And it's a similar story with the Doppler cut as well, where you have very similar performance of the ambiguity function, but your AFBM tends to have a lower side lobe level than the typical AFDM, so to say. And of course, we can now jump straight into the results for the receiver, because we don't want to spend too much time here. But the framework that we use for the communications receiver is a Gaussian belief propagation mechanism based on that filter time domain approach that we talked about before. As usual, all the details are in the manuscript, and this is how the beta rates compare against AFDM. As you can see, there's a significant improvement due to the better spectral localization, and also since we have a very low per subcarrier interference as well. So now this is a plot showing what happens when you have varying P. As you can see, when the P becomes lower, you have a slight decrease in the beta rate, but it still outperforms AFDM. And finally, we also designed a sensing receiver based on probabilistic data association tuned with expectation maximization. And this is also a message passing method based on the compressive sensing regime, where we try to estimate a sparse vector associated to the target parameters. And as seen here, the AFDM and AFBM waveforms have very similar performance, even in both in terms of range and velocity. There's a slightly better performance with AFBM when it comes to the range estimation, which we can attribute to the lower side lobes in the ambiguity function as well. So this is going to be our last slide, I think. Yeah, thank you for your attention. And do you have any questions?
Thanks so much, Ryan. Guys, any questions?
No questions.
Yes, I have a question.
Yes. Go ahead.
So first of all, very interesting idea. Could you go back to the slide with the out of band emission, the plot?
Yes, of course. Yeah, there you go.
So just for reference, I don't know if it's relevant, but how would OFDM compare to it? I see AFBM is quite bad, and then like your proposed method is really, really good. But where would you
Yes.
put OFDM?
So OFDM would sit right on top of AFDM in this
I
sense,
see.
because it's the same subcarrier structure, right? So you
Mhm.
you would have it right there on top of AFDM. And I mean, of course, there's variations of OFDM that you can do. For example, I've heard that DFTS OFDM, this uplink variation of OFDM, has better outer band emissions, but in general, it would still be significantly worse than filter bank modulation schemes.
I see. Yeah, that would have been my next question. Okay, thank you.
Yeah, you're welcome.
Thanks, Nicholas. I have a question too. Maybe it's a mix of a question and a comment. Now, filter bank modulation, conventional filter bank modulation is actually known to have a very high PAPR compared to OFDM. But here you are showing that actually, not here, but in one of your results, you show that the PAPR now is significantly better than AFDM. If I'm not wrong, if you can go back to that PAPR
Yes.
plot. Yeah. So you didn't plot OFDM here, but we know that OFDM and AFDM have the same level of
yeah.
PAPR. So can I therefore conclude that this filter bank modulation approach is perhaps the first example of OFDM-like, because AFDM is also in a way is an OFDM-like modulation. So this is what you're showing here, the first case, in my understanding, of a filter bank modulation scheme that actually has a lower PAPR than OFDM. Can you say about that?
Indeed, actually, I'm not so sure about the typical PAPR levels of FBMC systems in general. I would say they also probably are a bit lower than the traditional OFDM systems.
No,
But
that's not the case, man. This is actually known.
yeah,
You can look at papers, but this is one of the reasons why um, filter bank modulation is not widely used for conventional communication systems. You have to have very dedicated hardware to handle the high PPR of filter bank modulations.
yes, but if this is the case, then yeah,
Hmm.
I would agree that we can conclude that this AFBM scheme actually has both attributes, right? So it has a low PAPR and a good out-of-band emission
Yeah.
characteristics.
So I would suggest
Indeed.
that you investigate this a little bit. So go back to a classic filter bank modulation scheme and include in this plot. And of course, as already kind of hinted by Nicholas, also add the results for OFDM so that we have a more comprehensive comparison. Because if this is really the case, then this already is a compelling reason to look into this waveform more um, carefully as a
Yes,
possible candidate for new systems.
yes, I agree.
Any other
Okay.
questions, guys? I have one more question then. Could you
Yeah,
go back to the plot with the out-of-band emissions?
there you go.
Yeah, so here we see that apparently there is also somewhat of a choice, and it's a very significant choice.
Mm-hmm.
I mean, you have a lot of flexibility in adjusting your out-of-band emission. My question now is, what is the trade-off, right? So, for example, I would assume that when you use Hermite filters, you
Mm-hmm.
you reach this not so good compared to the Phi dice filter.
Mm-hmm.
So you have not as good an O out of band emission, but what you gain out of it, and vice versa. When you go to the other type of filter, what you have to give up in order to get so good.
So the fundamental difference is that this
Mm,
5DS filter is much longer
mm.
than the Hermite filter. So that's
Okay,
it.
so
So
rate.
yeah, yes, exactly. So you lose rate
Okay,
once you use 5DS filters instead
I
of
see.
Hermite.
I see. Understand.
Yeah.
And now, lastly, again, as part of this, the other example you show here, it's kind of difficult to see which one is which, but I think it's the solid line.
This
The spectrum
yes.
is actually narrower, significantly narrower. You have some kind of guard there.
Yes.
Can you elaborate more on that? Why would one do this at all? Why would you kind of sacrifice this? What's the application? Why would one like to do that at all?
So this small cut occurs when you have like a closer value of P to your number of subcarriers. So P
Mm-hmm,
is like the chirp index.
mm-hmm,
So when you have that almost similar to the same number as your number of subcarriers, then you would have a shorter, a somewhat slimmer frequency spectrum, and that's usually the case when that variation can also be seen here actually because
mm-hmm,
or maybe even here. Yeah, as you see here, when we decrease the P, we lose some bit rate performance, right?
mm-hmm.
So it's kind of like the same thing that's going on even in the outer band emissions because we are losing some frequency to work with.
Okay, but then the spectral efficiency might actually be, I mean, in the sense of beats per second per hertz, right? Because the BR that you showed there doesn't take into account the actual bandwidth. But if you
No.
by
Yeah.
by lowering the value of P, you also have a narrower overall bandwidth. A more fair comparison would actually have to take into account these
Yes, the
things
bandwidth as
normalized, right?
well.
Yeah.
Yeah.
Okay.
Yeah,
Cool.
true.
Anything else from you guys? If not, it's been enough time anyway. So thank you very much again, Ryan. And yeah, I see you guys again next time in the wireless channel.
Yeah, you're welcome.
Bye.